Okay. We are very happy to have Nabamita Banerjee with us today. She's going to tell us about mock modularity of the twisted index in CHL models.
Okay.
Yeah, please.
Thank you, Ramesh. And thanks to you for having me here. It's really great to be here, even if it for a couple of days, it's like excellent. So today I'll be talking on some properties that I will define the way I go ahead for some twisted indices in CHL models. Most of you probably already know these words. In case you do not know, do not worry. As I'll go ahead, I'll keep on telling you what they are. Okay. So the plan of the talk is following. First of all, I'll talk about why CHL models and why are they interesting, because they have a very special class of black holes in them, which are a very good platform for us. So I'll talk about those black holes in CHL models. And then this is a model, and these are some systems where studies are going on from, actively going on from 2005 almost. So it's like almost 20 years. So I'll tell you what have we learned about them so far. So the second point is basically going to be for black holes in CHL. Of course, we know much more, but this is only going to be for those. Then I'll tell what remains to learn, what we haven't learned yet, and probably we should be able to do that. And then I'll talk about, this is basically again getting back to the title, which says the mock modularity of the twisted index in CHL models. As I said, I'll define it. And then I'll finish by stating the importance of the study. And feel free to stop me at any point. Begin with, I must say that I'm a little sorry because the talk is a bit technical, although I'll try to make it less technical as much as possible. So stop me whenever you want. Okay. So black holes in CHL models. So as we know very well, that black holes are predictions of general theory of relativity, and they carry they have some thermodynamic quantities like temperature, entropy. We associate temperatures and entropy to black hole. And string theory as a quantum theory of gravity has been extremely successful in addressing the microscopic nature behind such properties. In past 20 years, as I started saying, dionic black holes that appear in this particular model known as CHL model, they have been extremely successful as a platform to explore many characteristics of black holes. So there are extended reviews on it, and if any of you are interested, you should go through them. I will only talk about some of the characteristics in today's talk. So what are CHL models? So there are many different ways to look at them. The one that I'll be talking about in today's talk mostly are type 2B string theories when they're compactified on this particular 6-dimensional manifold. M is some 4-dimensional manifold, which can be either a grade 3 or a T4, and times 2 circle. Such systems are very exotic, and the resultant theory is basically a 4-dimensional n equal to 4 supersymmetric string theory. One can actually further take some orbifolding at these two circles that I have written as Zm and Zn orbifolding of this theory, such that so when one takes such an orbifolding that not only acts on this, the two S's, it also acts on the internal space, and one has to take it such that it commutes with the supersymmetry, and then what it gives is basically a 16 with 16 supersymmetric charges system. And in the strong coupling of the theory, what one gets are dionic black holes. That is, one gets solutions. When one goes to the supergravity limit, one gets solutions which are black holes such that they carry both electric and magnetic charges. That's why they are called dionic. Whereas at zero temperature, if we go to that particular value of the temperature, that particular regime of the parameter, they corresponds to quarter BPS states. Okay. Now, the supersymmetry of the system actually helps us to compute the index in the weak coupling limit of the theory, where one can understand the microscopics basically coming from mutually free parts. And it's just because of supersymmetry that that calculation is possible. But again, because of supersymmetry, the results are valid. The whatever index computations can be done, those results are valid even at strong coupling, where there is really a black hole. And it has been proved that the same index basically gives the microscopic degeneracy of states of these ionic black holes that carry certain electric and magnetic charges. So the index has the information of the charges. Okay? That I'll make precise later on. Now, following usual statistical physics, the entropy, this microscopic degeneracy can actually be related to the entropy by taking the logarithm of the degeneracy, and it matches with the Bekenstein-Hawking entropy in the large charge limit. So, of course, these are black holes, so one can just compute their Bekenstein-Hawking entropy independently, and the two results matches in the large charge limit. Not just that, the equivalence actually holds to finer precision and gives us very good understanding of black hole microstates in this system. So since this is going to be important for us, let me just quickly tell you that what is this microscopic system really looks like. So at the weak coupling, as I said, this system can be thought of as mutually three different parts, three different free theories. And the configuration is as follows. One actually has one unit of Kaluza-Klein monopole. One can take multiple units also, but can be normalized to one as well. So we have certain Kaluza-Klein monopole charges associated with this circle S1 tilde. And then a D5 brane, where the D5 brane is wrapped on this space, on this 5-dimensional space, M cross S1, where M can again be either K3 or T2. Then one has certain units of D1 brane charge, where the brane is wrapped on S1, some momentum along S1, and some independent units of momentum along S1 tilde. Okay. So, of course, one can get more exotic configurations by considering various orbifolds of the system. And in the strong coupling, as I was talking about, this gives us a black hole that carries electric and magnetic charges denoted as Q and P, where Q square gets related to N, P square gets related to Q1, and Q dot P gets related to J, where all these guys are integers. And the entropy of these black holes are rightly produced from the degeneracy of the states that can be computed independently in the theory. So this is a very, very well-known result, I think, from 2006 or 7. Now, as I was talking about, that there are more exotic systems, and which are basically orbifolds of this system. The system that I talked about, it actually, if one goes to the modular space of M, then there one can find that there are more symmetries. It actually has a Zm cross Zn symmetry. And depending on that, I mean, how we are utilizing this symmetry, we can have following two situations. The case one that I call is twisted twinned case. In this case, only the S1 circle is orbifolded. Okay, so the momentum now doesn't go as N, but it goes as N by M. So what we are doing is we have only considered the Zm orbifold, leaving out the Zn. So Zn symmetry is still there. And this case also includes where the situations where GCD of M and N, these two is 1. This is one possibility. Even for these configurations, with these modifications, these charges and new symmetry generators acting on the system, one can compute the index. From the index, one can compute the degeneracy function. The results are known. And then there are doubly twisted case, as I call it, where both the symmetries, where both Zm and Zn orbifolding are done. So the momentum along S1 also gets changed to N by M units, and J also gets changed to J by N. So
act on
internet
translation or something along the circle.
Along the circle.
Also
act on the internal space. Yeah. Yes. Yes. So one has to take both into account to compute the index. So, and these are done. Good. So what we have learned so far for this system. Okay. So I hope the system is clear to you. If you have any question, please stop me at this point. Else I'll go ahead to tell you what is it that we already know.
What do you mean? two different circles?
Oh, yeah. So the theory that I'm considering is type 2b compactified on a 6 manifold where 2 of it are 2 circles. Okay, and so there is a possibility of orbifolding the first circle or the second circle or both the circles. And depending on what I am doing, and then if I go back and compute the Helicity stress index, of course modified with this when I'm taking this orbifolding as well, then the result will change. And that result will change, but nevertheless, the fact that that Helicity stress index is related to the degeneracy of the black hole is proved. So I can find the degeneracy of the microscopic degeneracy of the black holes. And then taking large charge limit, one can see that one gets back the usual thermodynamic entropy. No.
This can be done because the modular stress of M is
Symmetries. Yes, there are points which are invariant under this. Yes.
What value? What is this M?
Anything. Integer. Yeah, by anything I mean integer. I'm sorry. Yeah. No, so the results that are known are for some particular values of M and N when they are relatively prime. And for those cases, the computations are done. But nevertheless, the computation it would be very difficult. But so results for any value of M for n equal to, still keeping the second circle not being orbifolded is known. That is twisted twinned partition function, and that is what is given in this paper, 2010 paper of Sen. But when one orbifolds both the circle, that result is, there is some way to get to that also, given by Justin and Aradhita, but it's not very clear.
It's not that 1, 2, 3, 7, 8
So,
or something.
So for those, the explicit forms are also known. Yeah. So some of these results that one can write. So for example, this one is true for any M, any M and N where GCD of M and N are relatively prime. Yes.
K is that integer K you have put over there. Those are the ones which are, I think, restricted, right? The 5K.
This will be the weight. Right.
Yeah.
Right. So
that K you have not yet explained how.
I have not yet explained. Yes.
Not the same things which there is another CHL itself is parameterized by some orbifold. K depends on that.
No. So I can also consider CHL without taking any orbifolding. That's also the simplest possible CHL. That's like type 2b on K3 cross S1 tilde. Okay. For that case, this K turns out to be 10. Yes. Right. So for the 4-dimensional theory, it would mean that we are looking at black holes whose, okay, can I go back? See. Okay. So you see the correspondence with the 4-dimensional black hole is that it carries an electric charge and magnetic charge, where the electric charge squares to n and magnetic charge q dot p is j. Now, what the changes that would come here is this n will be replaced by n by m, and this j would be replaced by j by n.
For this co-prime values or the relatively prime values of m and n, results are known. You mean only the leading order entropy or?
No.
For example,
when I say results are known, I mean D is known. Okay. See, this is non-trivial. After that, what the computation of left-hand side is anyway completely independent from the right-hand side. But the interesting thing is, after taking large charge expansion of the right-hand side, one should get, one gets back, not should, one gets back left-hand side. Okay?
Even with the log correction.
Even with the corrections, exactly. For n equal to 4, it is not there, but for other systems, yes. Log corrections, power suppressed corrections, exponential suppressed corrections. It's proved to a very finite precision. Any other question? Okay. So is it clear? I'm going ahead. So what are known? I was just trying to say that. So for these systems, the degeneracy function is known. Please do not, for this talk, we really do not need all the details of the expressions, but I just wanted to say that it is known. It's pretty non-trivial and it is known. Okay. What is important in this entire expression is this C. Okay? So what does it tell us? It tells us that if somehow I can find a function phi, which is definitely a function of these guys, tau, sigma, and z, and then integrate it over along a particular contour, then that gives me the degeneracy of a state carrying particular charge, electric charge Q and magnetic charge P. But the subtlety here is the choice of the. How one chooses, how to choose this contour really depends on where in the tau sigma z plane, where I am really looking at for phi. And that is why this expression, although is extremely useful, but it is still not the best expression that we should look for, because there is still a choice related to it. I mean, one has to choose the contour case by case. Okay. So no. So they are related. Very good question. I'm sorry, I should have written. So Q is related to tau, Y is related to Z, and these are it will be in some exponential. Yeah. Sorry. Okay. Good. So it's there. Yeah.
If you restrict the previous slide, you restricted them to these. No. Yes. Even these ranges, are you saying the contour is?
Yeah, I have only restricted the imaginary values, no?
Yeah.
So just to understand what various quantities that were appearing there. So this tau sigma z is, I mean, one can just club them into a sigma which belongs to H2, and then these Q's are related to tau, Y is to Z, P is to sigma, and phi is a complicated looking function. And that also depends on it. It has an exponent A, which comes from an expression like this. It is nice to write, but it is not really very nice when one really wants to evaluate it. Okay, so it's like that. But that's the point is it is known. Good. And the coefficients, the one that is appearing here is for the first subscript being 0, but for generic subscript also one can find it, and the quantity that appears in the right hand side is related to the modified helicity stress index. So here this Gm and Zns are generators of Zm and Zn, and this trace is taken over all the twisted RR sector states in this particular superconformer field theory, and depending on in which one, either it can be T4 or K3. L0 and L0 bars are the left moving Virasoro generators. JL and JR are related to the U1 subsector of SU2s, asymmetric. Okay? I mean, all I'm trying to say is this can be computed, properly defined quantity, and people have evaluated. Okay, let me just go ahead. What is interesting here that I want to point out is that many interesting aspects of this degeneracy function that was completely independently predicted from ADS to CFT1 correspondence has actually been, we could actually explicitly test them using this model. Okay? So just from ADS to CFT1, one knows that how this index should behave. And then this is an independent calculation which really gives us back the same result. So it's really a very good platforms for testing the properties of black.
Part that you get from that is Kali-like.
Right. So right, and then okay. So since you asked, so the kind of thing is when one is orbifolding, when one is taking these orbifolds, then the degeneracy functions it changes. I mean, the change is pretty non-trivial, and from ADS to CFT1, one readily gets that. Right. Yeah. Right. Yeah. Okay. So so far whatever I talked about is again in the line of understanding more from the physics perspective, but there are more known to this system, and that just tells us that this degeneracy function actually has a very rich mathematical structure. In particular, this function, as I have already said, it's a single modular form of weight k of some subgroup G of SP4Z, and can be obtained by additive lift and multiplicative lift of an appropriate seed Jacobi form. It's an independent result. In fact, I should say that
Nabamita, you're assuming M and N are co-prime?
Yes, yes, Suresh.
Okay,
Please be
okay,
there.
thank you.
I will have something to ask you at the end. Please be there.
Yeah, okay.
Okay, yeah. So, so this was known, and I must say that the first time when this degeneracy function was really constructed, it was from this side only, and then people understood. I mean, then Ashok and that work was done by Jatkar and Sen, and then later David Jatkar and Sen also understood it from the physics side. So this is really rich in that sense, and then more recently, in the work of Dabholkar, Murthy Zagiar and Ajit, Ashok and Ranveer, they have shown that the meromorphic Jacobi form, which is related to this Jacobi form only, can be actually canonically decomposed as a sum of a mock Jacobi form and an Appel-Lert sum. While go ahead, I'll tell you what these objects are. Okay. Further, it tells that the quantum degeneracies of the single-centered black holes that arises in the ordinary and twisted CHL models are the Fourier coefficients of these mock Jacobi forms, and this has been proved for the case of m equal to 1 and for arbitrary n value. And the degeneracies of the multi-centered black holes, which actually decay when one crosses the wall, they are given by the Appel-Lert sum. So not just so mathematically, it has this kind of form, and then each form also has some physics information in there. Okay? And this decomposition, this last result is actually very important. Sorry, I don't know what I have written. I'm sorry. The decomposition actually does not work for all charge vectors. This was missing. This point was not clear. I mean, this point was actually misleading in the DMZ paper. But in the later paper by Ajit, Ashok and Ranveer, they showed that not all, this particular decomposition is not true for all charge vectors. There is a constraint on the charge vectors. Only for them, the corresponding degeneracy will have such property. The N, M, L, the quantities that I wrote, their values. So in general, they can be any integer, right? So black holes can carry any properly quantized charges, but these properties that I'm talking about is not true for the degeneracy functions of all of them.
I was just guessing, maybe you said that. So the charge vector should be like a multiple of n equal to 1.
It is, but what I'm trying to say, that, so what is this result? So they are saying that this, so in D, the quantity that directly goes is the Siegel model. Okay, but now what these people are trying to tell is, okay, do not just look at phi, but look at phi more closely. So when you look at phi more closely, you see that this Siegel modular form actually has the information of a Jacobi form, and that Jacobi form has information of more quantities, and that is this. It has a mock Jacobi part and the Appel-Lert part. This decomposition that I can always do, I can always find a mock Jacobi part, which will actually should come from a mock modular form that I'll state later on, is not true for all black hole states. Oh, this, right. I'll make it more clear exactly what decomposition I'm talking. Yes, Rajesh.
You have 1 over 5. So when you
yes,
it is for 1 over 5 that this holds of.
Yes, finally yes. For 1 over 5 this holds. Yes. Okay. So as I was saying, that this brings us to the question is what remains to learn. Okay. So as I said already, that this result. So okay, let me go back. So till this point, the results were known for any m and any n, but provided we are considering twisted twine sector and not doubly twisted sector. The partition function for doubly twisted sector and their further properties are still not properly studied. Okay? But at least the partition function is known for twisted twine sector. Now this part of the compute, I think the first part where the lift has been done is also known for twisted twined. But the fact that these degeneracy functions also has some mock properties into them, I'll define what it is only true for arbitrary n and m equal to 1. So of course it remains to know that if this is true, when one will have the twisted twine states or doubly twisted states. And if so, is the last point true? One expects it to be true because this is nothing but a special case of those cases, but then what constraints do they put on the charge vector? And finally, what constraints would it give us to the partition function or to the generating function of the black hole entropy?
The second point. What do you mean
Second, by second point, if
what do you mean by decay upon wall cross?
yeah. So when I'm writing down D, the degeneracy function, it has and as I said, while doing the integration, one has to choose the contour. So the result is valid within certain contour. And when one changes that, goes from one chamber to different chamber, there is a jump. The result shows that there is a jump. So D actually in it has the information of all possible states. Those can be single-centered black holes or those can be multi-centered black holes. But what this, and so upon choosing the right contour, okay, and being in a particular chamber, this formula tells us how to get the D, which will only correspond to the single-centered black holes. Okay. But this guy actually has all information. Phi k has everything. Right. And if you are following this definition, one can extract out the information of single-centered black hole from it. And yes, and single-centered plus multi-centered. Those configurations are also there. So one can take those, one can get those results also. So what this tells, what this tells is, when one, instead of studying phi, if one dig deep inside and goes to this Mock-Jacobi form and the Appel-Lash part, then these two really splits out this contribution. So then so if I then finally define my degeneracy functions of single-centered black holes with the help of the Mock-Jacobi form, then one doesn't need to really worry about the contouring. So in some sense, it's better, but well, as we will see, not in every sense. So for some computations, this is a better, well, this is an alternate, let's put it like that this is an alternate way of looking into it, which clearly tells us that which part should give me the multi-centered black hole contribution and which part should give me the single-centered black hole contribution.
What is the physical reason behind why this will segregate out? I mean, there's no reason to.
So yeah, I will show you exactly how they are different, and then you will see that from, I mean, to understand that, one really needs to go back to the system, understand what do I really mean by multi-centered black hole, when for a given set of charges, when I will have those kind of solutions, those kind of configurations. So yeah. Yes, Ashok. Yes, Rajesh.
But couldn't you work backwards and say for the charge vectors that don't obey this condition, where you don't have such a decomposition, you know that there is some contour that will give you the single-centered piece.
Right.
So can't you say what piece of the 1 over phi is contributing? I'm just trying to see if there's some way to
go it backward
and seeing for these other charge vectors, maybe it's not some canonical decomposition of this kind in terms of a Mock-Jacobi form, and but the contour integral is picking out perhaps only some parts of that.
Right. So it basically depends on, since that's a contour integral, we look at the polar structure of that function and then take out contributions appropriately. Yeah.
So then doesn't that define for you?
It is actually this Appel-Lash part is basically the singular part of the function.
Okay.
So.
But then for charge vectors which don't obey this decomposition, can't you use that criterion?
Okay. So one can. So I should refine my statement. In in DMZ paper, the statement was when the magnetic charges are greater than the electric charges, then certain decomposition always works. Okay, that statement is not correct. So decomposition, it is, so it is that particular
decomposition, but
it is not that particular, I mean, it is not the same decomposition which will hold for all n and m such that n is. Okay. Good. So as I said, then what remains to really check is if this non-trivial constructions really goes through for this system. Okay. And I hope it is clear by now that if we want to understand these structures, we really need to look at the partition functions and their mathematical properties in details, and that is what we will be doing next. Okay, so next few slides I'll again introduce what is modular form with modular form, Jacobi form, single modular form, and mock modular form and mock Jacobi form. But these definitions are not really very precise in the sense that I will not tell you all the properties that these functions must have. It will make my slides and the talk even more technical. But the proofs that people have done are definitely very concrete. So all properties have been taken into care, and then only the statements are made. I'll try to tell you the prime ones and not all the details. Okay, so let us just consider SL2Z matrix ABCD and then take any point on the upper half plane such that on that point any element of SL2Z will act like this, and then also just take a function that maps from H to C, and then we define an operator for any integer k. K can be even integer or integer or half integer, half integer also. And the operator is such that the slash operator f slash gamma tau is defined to have this kind of a property. So let's take this. This is our definition of the operator. Various quantities appearing here are well-known objects. So I have noted what they are here. And for positive integer n, one can actually define various finite index subgroups of SL2Z. So these are some. Gamma lower 0 is the one where C is modded with n. The upper 0 is also an important one that appears and is important for the calculations where B is modded. Gamma 1 is again C modded with A and D being one mod n. Gamma upper 1 would be the same thing, but instead of C it would be B, and gamma is the subgroup where all of them are constrained. So it's easy to understand that these forms subgroups. And this n is what defines the index of this subgroup. Okay. Now, let us go ahead a bit. So far I just talked about the property. I defined some operator which was acting on a function that was just mapping from H to C, upper half plane to full complex plane. Now, let us go ahead and define another function which will map from H cross C to C, and such that for them also we are defining the operators such that when only I am changing the element of H2 tau, then the transformation is like this. This is known as modular transformation. But when it is acting on the second argument that belongs to entire complex plane, the transformation is like this. This is known as elliptic transformation. Okay? So we are just defining different operations on functions. With this, yeah. I'm sorry. I thought it is so obvious. I'm sorry. Yeah. Okay. Now, with these two definitions, the modular forms are holomorphic functions. Let me define, and then I will relax the conditions. So, a holomorphic function f is called a holomorphic modular form of weight k if f slash gamma is f. Okay. And for every gamma, which belongs to some subgroup of SL2Z, and f is holomorphic at all the cusps of gamma. Now, this holomorphicity is not really needed. Okay? So if the function is not really holomorphic, but it's weakly holomorphic, then also this is true. If the function is non-holomorphic, then also this is true. And the only change is it must vanish at all the cusps. That is the property that it must satisfy. And if that is true, then we will call them modular forms or weak modular forms or cusp forms. Okay? Some subgroup of SL2Z. I'll tell you later on. That is why I was not trying to. I'll tell you. Okay. Now, Jacobi forms. Okay, Jacobi forms. I hope you have understood that these are those functions. Again, holomorphic Jacobi forms of weight k and index m are those functions for which the second operation that I just defined, the modular transformations and the elliptic transformations. Under both the transformations, if the function does not change, then we will call it a Jacobi form. Again, it can be holomorphic, it can be weakly holomorphic, it may not be holomorphic at all. When I'm giving these definitions, like here I said that how it should behave. So cusp is the end point, basically. So here, basically, I need to tell how the functions are behaving when I'm going to the boundary of the space. And they should be well behaved. They need not be zero, but they should have right kind of a fall-off conditions. So those are also needs to be specified. Okay, good. Now, what is a Siegel modular form? So let us, because we saw that the object that appears in our computation is a Siegel modular form. So as for defining a Siegel modular form, we need to extend, we need to go from upper half plane to 2 copies of upper half plane. And we do it like this. So here tau and sigma both belongs to upper half plane and z belongs to the whole complex plane. And all these omegas are constrained by this condition that this must be true. Okay. Now you take any matrix M. Okay. So basically trying to extend the definition of modularity, which was for functions from H to C to this case. Okay. So we also need, there we only needed matrices from SL to Z. Here we need matrices from SP to Z. So these guys act on omega like this. So it gives us A omega plus B plus C omega plus D inverse. And of course, they have to be, these are symplectic forms. So A, B, C, Ds are not absolutely independent. They satisfy certain conditions, like in that case, AD minus BC was 1. Here also these are constraints. But we know that. Okay? Those are known. Now let's take a function which is mapping from H2 to C, and again define a weight K, which can be any integer / operator of this kind. Okay, so the operator, what it is doing is when M is transformed, sorry, omega is transformed via M, then the function is changing like that. Okay? And I hope you have understood that we will call a function, we will call the function to be a Siegel modular form if that remains invariant under this transformation. And that's what it is. So let G be any subgroup of SP to Z. So a holomorphic function, this is called a Siegel modular form of weight K for G, if this is true. Okay. So what remains to understand or what remains to find is what is this G. So it need not be, I mean, it is definitely not the entire group, right? So we need to find a subgroup under which this property is holding. Then under that group, it's a Siegel modular. Is this point clear? That is what is, little non-trivial. It can be, yes, it can be. But in non-trivial cases, it is not. And that's the actual, see, I mean, when I already know the function and I want to understand its properties, then the non-trivial part is to understand what is this G. Okay? What are, first of all, what are the transformation that is keeping it invariant? And then what are the group operators that is generating that transformation? Okay? So that's the non-trivial part when I know the function and want to understand its properties. In this case, that is where we are. We already know the function because the partition function is known. Okay, good. So, so what, with these 3 definitions, now I will tell you that why understanding this sort of properties of the function is interesting or is important. Okay? So what the Siegel modular form and the symmetries and the subgroup that keeps it, that does not change this function phi, makes it a Siegel modular form does for us is following. The modular property of the Siegel modular form actually imposes periodicity to the functions. So see, what is this statement? It is telling me that when I'm changing omega, phi is not changing. It's some kind of an invariance property, right? So it will then tell me that how, when sigma, tau, and z are transforming, such that the function is not transformed. Okay? So it will give us certain periodicity conditions on the function, and that in turn allows a Fourier decomposition of the set. Okay? Fine. Now it turns out that when we decompose this function in the sigma variable or in the tau variable, the coefficients of decompositions actually transforms as a Jacobi form of weight K and index M under the subgroup gamma cross Z. Okay. This is a result that one can prove. I mean, they have proved it for the cases that I told you for M equal to 1 and any n. So what I'm trying to say is that this phi or 1 over phi can actually be expanded as some function of say sigma tau and z times exponential of 2 pi I v some m. Okay, there would be constants on m. This is phi k. So this particular decomposition is guaranteed by the first line. Once I know what sort of a transformation properties it satisfies, and what is non-trivial is once you get it, one can actually check that these guys are themselves richer and they're actually Jacobi forms. Okay? This statement is non-trivial, and once we identify the subgroup properly, this part can be proved. Okay?
The 2 pi I sigma.
Nah, it is a 2 pi I sigma, yes. Okay? Good. So please keep this in your mind and let us take a step ahead and understand what are mock forms. No, so take any smooth functions, f, which is a map from H to C, and it is, first of all, it is called a harmonic mass form of weight k for the group gamma if, first of all, it's a modular form, and then second, this particular, this is called, this is Laplace, but weighted Laplace with k. If it is a zero modes for those operators, then if both the conditions are valid, then such a function is called harmonic mass functions or mass forms. This is, of course, again, as I was saying, along with this, it has to satisfy certain follow-up conditions. Now, suppose one splits f into two parts, f plus tau and f minus tau. How is this splitting done? The first part is holomorphic, and the second part is whatever makes it non-holomorphic. With this decomposition, let us define some other object which is known as mock modular. So a mock modular form of weight k is the holomorphic part f plus of a harmonic mass form of weight k for which f minus is non-trivial. So one must have a f minus. So this definition is for functions which are themselves not holomorphic. It has a piece in it which makes it not holomorphic, but nevertheless, its holomorphic part satisfies some property, and that's what we are trying to understand. Okay? So a weakly holomorphic modular form, this is basically a shadow transformation of this, is called the shadow of the mock modular form F plus. So if I know the mock modular form and then act on it with this known shadow transformation function, this is actually del tau bar. It gives me a mock modular form. It gives me a weakly holomorphic modular form. So the harmonic mass form F is called the completion of the mock modular form F plus. Should I just write here? What I'm trying to say is, suppose take a function again, F, but this is not holomorphic. So I'm splitting it into two parts. This is the holomorphic part of it, and F minus is whatever makes it non-holomorphic. So I need to understand how to get this piece. Once I get this piece, I can uniquely define what is F plus. Okay? Once I know F plus, and then act on it, this particular operator, which is known as the shadow operator, like this delta operator, the form of the shadow operator is also known. This on F plus gives me a modular form. Okay? If this is true, and if there is a non-trivial F minus, then F plus is called mock modular. So it's not modular, but it tells me how to get a modular form.
The shadow operator that we see already.
Yeah, I think it is del tau bar to some factor that I do not remember. I'll tell you. Okay?
This decomposition is not unique F plus plus F minus.
No, it is. So if what is non-trivial is to understand what is F minus. And once I know what is F minus, then everything remaining in F is F.
minus itself is.
So I need to tell you how to find F minus and when that can be done, right? That's the non-trivial part of it.
Nabamita, y is im tau, right? In
Sorry,
that
Sunil?
Laplacian. Y is imaginary part of tau, right?
Tau is x plus iy, yes. Sorry, yes. Okay, so let me just reiterate it once more. So a mock modular, you might be seeing here a word pure because this definition is really for pure. And that also tells us that there is something which is not pure and those also appear. But let us not get into that kind of details. So a mock modular form of weight k is the holomorphic part F plus of a harmonic mass form of weight k for which F minus is non-trivial, as I said. And the weakly holomorphic modular form, this is called the shadow of the mock modular form, this of F plus. So the harmonic mass form F is the completion of the mock modular form F minus. So I should be able to, one should be able to uniquely determine what is F minus and find F plus, and then it is guaranteed that the sum of it would be a harmonic mass. These are I'm sorry, I'm not a mathematician, so I'm probably not making the statements as it should be, but these are theorems and has been proved. Okay? Yes.
Is it the case that when F minus is not there, which is
it's trivial, yeah.
Then my mock modular form will be modular?
Modular, yes. Okay. Now, let me say what is, I already told you what was the result of Davalkar, Murthy, Zagiar and this paper by Ajit, Ashok and Ranveer, Bhan, Sen and Singh. Okay. But let me tell now that how to get to their results. What are the steps to get to the conclusion that they have obtained? And if you remember, their conclusion was that there is, so the Siegel modular form has in its meromorphic Jacobi form, and the meromorphic Jacobi form actually gives us a mock Jacobi form, where the mock part of it gives me the single-centered black hole entropy and the Appel-Lars sum part of it gives me the multi-centered black hole entropy. That was their result. Okay? So let me tell you how to go for it. So the Fourier Jacobi expansion of the relevant Siegel modular form first gives us the meromorphic Jacobi form as its Fourier coefficients, which are basically these guys. So I'm starting with this. First understanding is transformation properties, and from there we are identifying what is the Jacobi form. And as it turns out that they are in general classical Jacobi form, so they need not be holomorphic functions. And in this case, for the two cases that they studied, this turns out to be meromorphic. Now, the Jacobi form can actually be shown to be sum of two distinct functions, namely a finite part and the polar part. So that's like this. So if I, okay, so here the thing that I wrote are for modular forms, but let us take a Jacobi form, m tau z, and suppose it had two parts in it. I'm calling one to be finite and another one to be polar. So let me define what they are. So the polar part, by definition, are the singular parts of the Jacobi form when you take z goes to 0. Okay. So now, so here, if I know the function, then I can just study its asymptotic behavior when z is going to 0, and I can identify what the polar part is. Okay. Now, once the polar part is subtracted, the remaining function is defined as the finite. Okay. So up to this, it is definition and just construction. Next point is non-trivial. Now it has been proved that if the polar part contains only single and double pole at distinct points in the complex plane, then the finite part is a mock Jacobi. It's only true when the polar part is singular only up to a pole, single pole or a double pole, and that too just at distinct points. It is just the singular part of it. That's how I define it. So the regular parts I'm not going to take. And this basically, this implies that, so this is a theorem. And then what the implication of this theorem is that once it is a mock Jacobi form, one can actually have a theta function expansion of these Jacobi forms and the coefficients of that expansions and mock modular forms. Okay. The finite part gives us the entropy of the single-centered black holes, and the polar part, this is the apple-lash part, gives us the entropy of the, not entropy, the degeneracies of the multi-centered black holes. Okay. I mean, that is definitely a second part of the proof. One has to prove that. But this is the way to get to phi p and phi f. Is it clear?
Nabamita, are you looking at the Fourier Jacobi expansion of 1 upon phi?
Yes.
Okay.
Okay. So now let us get back to the twisted index CHL models. So I hope that the idea is clear. So as it was shown in this paper, which is basically an extension of DMZ results, the proof is, sorry.
Okay, but the third point, you mentioned 3 points there earlier, right? One is this, the fact that there is contribution from single center, other is multi-center, and
You were talking about the charge vectors, yes.
What happened to the third? We didn't get to the third point, right? We didn't find the chart.
So what will give me that constraint? Okay, I'll tell you. So here what this n, okay. So this taus and the powers of tau and so this m basically, and so this thing can also be done because I know its transformation properties with respect to all its variable, right? Sorry, the left hand side. This is a function of tau, sigma, and z, and I know how it transforms with respect to all the variables. So one can do this decomposition for all the variables. The decomposition with respect to sigma, the interpretation is that this m is related to the magnetic charge of the corresponding system, black hole. Whereas if I would have done it with respect to tau, that would be electric charge of the system. Okay? Now these m and n's are, now I also know that in my system, there are transformations that relates as electric and magnetic charges. Okay? So although I am getting results from two different expansions, they must match because physically they're the same system and they must match under the right S-duality transformation. That imposes. So, good question. So, see, we are first of all talking about the black holes that or the quarter BPS states in CHL. So, the charge lattice that I started with was very specific, but there are works where one has generalized it to as much as possible. But of course, this is not the most generic charge lattice, and for the most generic charge lattice, the results are not. But to a good extension of charge lattice, the results are. Known means it's basically the same result. The result extends. Okay. Good. So this extension for DMZ paper, I mean for m equal to n equal to 1 to non-trivial n was already pretty non-trivial. But pretty non-trivial is not the point. I mean, this basically requires refining the mathematical theorems. But what it gave us, that this analysis told us that one can identify some charge vectors for which this above the decompositions that I was talking about and the mock modularity property is not valid. That was an important outcome of this analysis. So what we expect is same thing to be true for the twisted twined states in the CHL models. And we went ahead to do the calculation. So this is our result so far. The analysis is not complete, and I'll tell you which part remains to be done. So we started with the sense partition function and the corresponding Siegel modular form. For us, the starting point was easier in this case because we knew the partition function. So second step was non-trivial, where one had to identify the subgroup of the full modular group that keeps it invariant. When I say it keeps it invariant, first point was to understand how does it transforms, under what sort of transformations it should not change, and then to understand what are the generators what are the group elements which will generate those kind of transformations. Okay, this is non-trivial, but once this is done, then using the symmetry properties, the meromorphic Jacobi form has been found. And then a further extension of BSS results we have been able to do, the theorem extends, and we concluded that even for this system, the classical degeneracy function satisfies mock modularity. The set of charges are identified for which the degeneracy function has this kind of a behavior. So basically the entire results goes extends to this system as well. Any question?
Charge vectors for which modularity is valid. Is there something special about them from the point of view of physics? You kind of just
See, okay. That is what we want to understand. So far, we only have data. Do not know anything more than that. But we want to understand that if these charge vectors can tell us something more about the system. It should, but not clear yet. And the whole point of studying these two other systems was to see if we can get something more. I mean, if we can see some pattern, not yet. Yes.
For the charge vectors for which this does not hold, you don't have small modular behavior at all. The D is still low.
D is still no. Yes, yes. So all I'm trying to say, a particular decomposition is not going to work. As was predicted by DMZ is not. No, yeah, not yet clear. So we could see how they are in the charge plane, but yeah, they're not clear. Let me just say that.
There are regions where I guess, no, sorry. For a certain charge vector in the charge vector space, aren't there regions where you only admit single-centered black holes without multi-centered?
Yes.
Those are different regions.
Those are different regions. Now, what I'm trying to say is, so
this is all, sorry, this, so everything you're saying is in the regime of charge vectors which admit both single and multi-centered.
And multi-centered, because
So,
F minus
okay,
must be
so
non-trivial.
you're not considering the ones which, so this decomposition that you're talking about is in a regime, is in a region of the charge vector space where you can.
It is non-trivial, yeah, where there is something really mock, yeah.
Generic behavior or the failure of mock modularity? What is it?
No, it's I wouldn't. It is not failure. So okay. So
for most charge vectors, mock modularity holds, is it?
For a wide, yeah, for most of it holds. So what? Okay, I should probably make the statement clear. DMZ said that when the electric charges are greater than magnetic charges, certain kind of a decomposition would hold for all such states. That statement is not correct. So there are further constraints on the system for which this is going to be true.
But so what remains is that a set of isolated charge vectors for
Yes.
mock modularity.
For which this does not hold. For most of it, yes. For most of it holds, but there are some for which it does not hold. And then if we, I mean, the whole, okay, let me come to the
I'm just
conclusion.
curious how this BSS discovered that they were the ones who discovered.
So they were just finding this the corresponding mock properties, and then when they were doing that, so as I said, right, so this n and m here, these are just some parameters, but when I'm going back to my physics systems, I know that they are something, I mean, they are physical quantities, and I have S duality to my system. So whatever results I'm getting, that should be consistent with the S duality transformations. When they applied that, they found that something is missing.
It's not that the mock modularity fails in a finite number of charges. There's no such argument.
No. It's just some generic decomposition is not correct for a large class of charges. It is that kind of a statement.
It's not that we do not know like which one is bigger. Just to continue.
Which one is?
Like mock modularity, is it a generic behavior? Is it, or is it like?
It is a generic behavior for a whole class of charges, but not all charges. So see, okay.
No, I'm asking.
Let me answer his question. Okay, please complete.
I'm just asking, like, is it like, you know, the points at which the mock modularity fails, is it a set of measure zero? That, you know, precisely asking. I don't think there's any statement like that.
No.
Yeah.
No.
So it just could be infinite number of points. And
Could be.
yeah.
Could be.
And
No,
then any countable infinite number of points are the same as any other countable infinite.
Yeah. Yes, only few have been. Yeah, I have to refine the statement. Let me just think. How can I do that? So, okay, just give me. Okay, no, it's okay. I'm just trying to think how to tell you. So let me. See, as I was telling that these guys can be expanded like this, or it can also be expanded, say, suppose in terms of a different function, psi, some n, okay, now sigma nz, and exponential of 2 pi I tau to the n. Okay, so the results are this, that if I take these two meromorphic Jacobi forms and find the corresponding mock Jacobi form for these guys and for these guys, let me call the one that I'm getting from here to be phi f and the one that I'm getting from here to be psi f. This gives us the degeneracies for systems for which I think n is greater than m, and this gives us the degeneracies of the system for the states for which m is greater than. Yes. Now, suppose, what about those cases where n is equal to m? Okay? Then I should be able to show that they're same. So, and for those cases where, for those n and m's which are related by s, so I should be able to show that they are connected. So this study puts constraints. This is the precise study. And yeah, I would not make further because this is what I know.
For those n equal to n for which these don't have.
Yes, I would say that they do not have this kind of a thing. Okay?
This is the like S duality we expect from.
Right. So, importance of the results. So far we have been able to identify the SIT functions for multiplicative. I did not talk about it here, but this is also interesting for the multiplicative lift and additive lift of the degeneracy function. And the construction definitely gives us new mock modular form. So that is why I think this study is interesting even just from purely mathematics side, because this gives us this function. I mean, we know they are defined, but it is nice to find examples of them. And we have now more examples of them. It would be interesting to see, and the second point I find is interesting, and hence saying that it would be interesting to see if the extensive modular properties can tell us something more about the seat functions. Okay? I mean, seat functions, so once I have the partition function, there is a way to construct, to get to it by starting from a function and then doing something which is known as multiplicative lift or doing something which is known as additive lift. Okay, they're very different prescriptions, but finally gives me the same thing. Now, I know that the final function, the degeneracy function, has this rich structure. Would it tell us something about the seat function? And if it does that have any importance in the context of my physical system? Do not know. I do not know the answer, but I think this is interesting. Okay, now here, Suresh, are you still there?
Yeah, I'm there.
Okay, so here it is worth mentioning that our additive lift particularly is not matching with Suresh's. So
For which examples? For which ones?
twisted twined.
Yeah, like give an example.
Give an example. Okay, so for me,
For-
so for any m and n, okay, but GCD of m and n to be 1.
Okay.
I'll talk to you later on. Okay, but just to tell you that it's not matching.
Because we checked that the product and the sum formulae agree.
Oh, yeah, I have got it from both sides, and your result is from additive side, from additive lift. It's just
No, I have checked. I have checked that they agree, both.
Achha, I'll talk to you later.
Okay.
And so one obvious next step would be to expand this analysis for doubly twisted sector. Yeah, I mean, mathematically dirty, you will give us more function. I like it. So not bad. And probably interesting also because maybe it will tell us something more about the charge vectors and this particular kind of structures. And border goal would be to gain further insight into the symmetry of the system so that we can have a better understanding of the partition function. By that I mean that our final goal is to somehow write the degeneracy function that will tell us, that will give us the microscopic degeneracy of the system. So far the two forms that we have is one where we have to integrate over, it gives me the result for any Q and P, whereas in terms of this, and depends on the choice of contour. And in terms of these functions, it gives me the results for any electric charge or any magnetic charge, because the other one is summed over. So, and we see that it also tells that this cannot be done for all the charge vectors. So can we come up with some expression where I will have a definition of a generating functional which is like, which does not have this sort of an issue, or which knows already this sort of informations into it. I know it's very vague, and I'm sorry, but yeah, that is what probably would be good. I think that's it. So thank you.
Questions?
You had another question at some point that I said I'll tell you later on. Let's go back. Okay. Let's go ahead.
There's this index equal degeneracy kind of state that you are also assuming, right?
No, I'm not assuming. You can prove that for this case, the quadrivial says that we are working, the index is equal to D.
Yeah, so the right hand side that you write in this D equal this, that is really some index thing.
That is really some index.
And the fact that it's degeneracy, it's just a check.
And it need not be the degeneracy for us. For this distance, one can prove that it is the distance. This is again same.
Yeah.
2008.
Okay.
So we are still in this. That is why I think this particular model, the CHL is very good, because it is, well, it does not give us any log correction, that's different, but other than that, it is very good.
So I had some additional point. What is the twisting you are mentioning here? This is not the twist people usually talk about in this SUSE constructions, right? You're talking.
For my definition, it's exactly what I do. So before twisting, suppose the S1 circle radius is 2 pi n.
Yes.
After twisting,
After twisting, it's 2 pi.
I'm just modding out by n. And
Just this quotient.
quotient.
Oh. Okay.
And yes, this as well as since I'm looking at the system with certain supersymmetry, and this Z is not only going to act on it, it is also going to act on the internal space, modular space in. So one has to take that also. Both together is twist. And for
How is that related to the decomposition we're talking about?
For being absolutely mathematically precise, you should look at the left. Okay? Because I'm not writing every point. I'm just giving you the outline. So let me start from here. What I know is D. Actually, what I know is this function phi. This goes into this D when computed for a properly chosen contour gives me single center black color. If you do not do it properly, then you get contributions where there is single center as well as. Yeah. Okay, that is one side of this. Now come here. From this phi, okay, I can actually get Jacobi. This is a single one. Is this room? Can you continue here or I should go? So from the single modular form, I can get a Jacobi form. This Jacobi form, if it was a holomorphic Jacobi form, life would have been easy. But because holomorphic Jacobi forms can actually be expanded in terms of theta functions. Let me say it's a function of tau and z as I was taking. These guys are functions of tau and these guys are functions of z, but these are theta functions. The Jacobi. where one can then show that these guys, if this is holomorphic, then these guys are mock modular. Okay? But in general, the Jacobi form that one will get need not be the holomorphic. And it turns out that for our case, it is not. Those are meromorphic. Since those are meromorphic functions, it is definitely, I should not be able to expand it in terms of theta. Right? So one cannot do that. But what one does is following. They say, okay, let us write a part of it that has a theta function decomposed, which is something. This is a part of it. Of course, then I will have something else here. This side. What one can show is that this part, which comes from the Bell sum or the polar part, they are defined. I mean, this part is always such that it contains the information of the singularity of the function when one goes to z. So from that study, one can at least understand what these guys are. And then can understand what these guys are. From here, one sees that, okay, so these quantities now will again be my mock modular form. And the statement is that the information of single-centered the information of the multi-centered black holes is. Okay. Now you may ask, I mean, what we like to understand is, okay, so what? I mean, what do I get out of it? Isn't it? So, I mean, one should not be doing everything to get to this, and it is not even needed. So you can actually define this HS directly from. I mean, when I say you can, means those are proved. Okay, these are theorems that with this one can construct it. With the asymptotic expansion of this, one can construct it, and then one can actually show. So one can construct both of these, and then one can show that this plus this is really giving you back the full function, which is a meromorphic. So it's not just the equality at the functional level, but also their properties. Because you see, I mean, when I am identifying it, I am identifying it by taking z going to zero limit. But then I am making a statement which is true for any tower. And so I need to do the transformation and come. That's it. So the statement is that black hole degeneracy functions, although need not be always modular, but at least they are modular. At least the single-centered black hole degeneracy functions are modular. It's not. We would be happy if it is modular, but it is not modular. I mean, if it is modular, then it has. What is the benefit of something being a nice function, a nice transformation, right? But it is not modular. Nevertheless, it is more modular, and hence still it has nice transformation. That's the. I mean, that's the outcome of this.
Yeah, but this decomposition is unique so far, right? There's no problem.
Only thing, if you ask me technically, what goes into the calculation is first be very good and get the partition function. We have not for Zm cross Zn non-fold. I still don't know the partition. That's the hardest part, I think. The part that we have solved for that, Sen already found the partition. Okay, that's the first. Second part is to understand what are these invariant. That is pretty not. It is not at all. And one has to, we actually finally could get it by writing that function in terms of some integrals. That is called threshold integrals. From there we could understand. So first of all, getting the function is not trivial. Then writing it as threshold integrals, performing integrals, and showing that it is really giving you back the function is not trivial. In this case, both were known. And then we understood, I mean, what we could do is from those threshold integrals, we could understand that what are the transform, what are the invariance properties of the function. Once we get it, then identifying the group was with Ranveer was much easier. After that, basically, BSS extends. ML in GCD of
GCD is one. Just go
relativity.
For that, the partition function was known. Some direct computation.
Yes. From physics computation. So what Suresh et al. Have done it is they have written the partition function from just by mathematical construction. And what I see is that he may not agree, and I have to talk to him again, that does not match with the physics part. So of course it was not matching with my limb. If I have done that correct. So what to do? Is this, should it just remain like, if you have more questions, please go.
Just this final cusp thing you were going to.
I would need to
Okay, we
show
can-
you something.
Okay.
Okay, if there are no more questions, let's thank Nabamita again.
Not yet. I want to, wait,